This lecture is about horizontal curves and how we compute them and how we lay them out. A horizontal curve is simply a transition between two tangent alignments. Here on the screen you see two tangents that are intersecting, and we can fit a circular curve between them. This circular curve is tangent to both of these tangent elements. That is, if the curve made a complete circle, then the curve would come in contact with each tangent at one distinct point. That is, the curve is tangent to each of the two straight lines that you see here. We have three primary control points that help describe the relationship of the curve and these two tangents. The first is the point of curvature, the second is the point of intersection, and the third is the point of tangency. The point of intersection is the location where the two tangents intersect. The point of curvature is the beginning of the curve, and the point of tangency is the end of the curve. In other regions, you may see this described as BC for beginning of curve and EC for end of curve. The station of the point of curvature is smaller than the station of the point of tangency. That is, stationing increases from the point of curvature to the point of tangency. There are several geometric parameters that describe our curve, and we need all of these in order to not only compute the way we will lay out the curve, but to actually do the field work. So we have central angle, radius, tangent distance, degree of curvature, external distance, middle ordinate, chord length, and arc length. I've got these spelled out for you here. The delta angle, or the central angle, is that angle defined by the point of curvature, the center of the curve, and the point of tangency. It is simply the angle swept by the curve from the PC to the PT. The tangent distance, T, that you see at the top, extends from the PC to the PI. It is also the distance from the PI to the PT. Because this is a circular curve, that T distance occurs in two places. The chord length, C, extends from the PC to the PT, and it is by definition shorter than L, that is the arc length. The middle ordinate distance is that distance from the curve midpoint to the midpoint of the long chord, that is the chord going from the PC to the PT. The external distance is simply an extension of the middle ordinate. It goes from the arc midpoint to the PI. This is a useful measurement to make during layout to ensure that the layout is progressing as it should. A few other relationships are handy to remember, and probably the most critical one is the fact that the angle between the tangent line that you see labeled there and the long chord from the PC to the PT, that angle is delta over 2, or half of the central angle. You could say this is the deflection of the PT relative to the PC and PI line. Traditionally, we have laid out curves by occupying the PC and sighting the PI, setting 0 at the PI, and turning deflection angles. This is a useful way to learn the geometry of circular curves, yet in reality, these days, we often will stake these curves by occupying points not even on the alignment. That requires that we know the coordinates, or we compute the coordinates of our layout points on the curve, and thus use electronic data collection methods to compute layout angles and distances from some remote layout point. Further, we may use GPS, staking out the points that we have computed in coordinate geometry routines to establish this curve. Another parameter that was on our list just a few slides ago was the degree of curvature. The degree of curvature is that portion of the central angle swept by a 100-foot arc. Here are a few of the equations that describe the relationships between the curve parameters. We will use these in conjunction with each other, and I encourage you to consider that any equation that has two variables can be used to solve for any of those variables. Here are the remaining relationships, and you'll notice that there are multiple ways of finding each parameter. So let's start with a circular curve example problem. It is not uncommon to describe the position of a curve primarily by its PI station. This particular circular curve has been described with its central angle and its degree of curvature. It could have been described with its t distance and a radius, or a long chord and an arc length. Nonetheless, we know that when we have any two of the primary curve parameters, then we can calculate the remaining parameters. In our case, delta and d are the two curve parameters we need. The PI station is not a curve parameter, is what locates the curve. So it doesn't define the shape of the curve, it only defines the position. Therefore, delta and d are our curve parameters. So, step one. In order to do this, we need to calculate all our remaining curve parameters. So we'll come up with the radius, the tangent distance, the arc length, the external distance, and the mid-ordinate distance, and then the PC, PI, and PT stations. In our case, we already know the PI station. So we can simply use our equations that are listed in the previous slide. And here you'll notice we can plug in the degree of curvature to this first equation and come out with the radius very directly, 823.50 feet. Tangent distance we get from the radius and the delta angle. We plug them in, then you'll see the radius we get is 514.58 feet. The arc length is related to not only the delta angle, but the degree of curvature. And those two angles, the delta and the degree of curvature, were our two inputs for this curve. And that gives us a total arc length of 919.86 feet. The external distance depends on the tangent distance and the delta angle. Here you can see we have plugged them in to give us an E distance of 147.55 feet. The point of curvature station is dependent on the PI station. The PI station minus the tangent distance gives us the station at the PC. Now, this may seem a little confusing at first. Let me explain it this way. The station of any point on the curve is measured along the arc length. However, the exception to that is the PI is stationed along the extension of the first tangent that defines the curve. This is different than finding the station of the PT. The PT station is defined as the PC station plus the curve length. This makes sense because we want to station the curve along the arc. The difference between the PT station and the PC station should be the curve length. Now, if you took the PI station and added the T distance to it, you would not get the PT station. It's very important to understand the T distance does not relate the PI to the PT stations. The T distance is the difference between the PC station and the PI station. When we've computed these parameters, you can see the results summarized here. This is what the curve would look like. You can see the PC station label on the left, and the PT station labeled on the right. The PI is a point that does not fall on the curve. Notice that the PI station of 58 plus 3742 is likely greater than the midpoint station of the arc. You can see that the midpoint station of the arc, if you were to estimate it, is less than 58 plus 00. However, the PI station is greater than that because the PI station is related to the PC along the extension of the tangent on which the PC lies. So as we start to lay out our curve, we're going to lay it out relative to our line between the PI and the PC. So here you can see the PC on the left, the PI on the right, and we'll set up the instrument at the PC and set 0 on the PI. And our task will be to turn deflection angles and measure chord distances from the PC to each of the points that you see here at 54 plus 00, and 55 plus 00, 56 plus 00, and so forth. As we continue on in that process, you will see that we're simply measuring deflection angles and distances as we progress through the curve. When we get to the end, our final deflection angle should equal half of our total swept angle, or central angle, that is, delta. And the chord distance from the PC to the PT, in our case, is 872.78. So once we have calculated all the primary curve parameters, our next task is to compute deflections relative to the tangent. That is the tangent between the PC and the PI. First, we will compute incremental deflections. Then we will compute total cumulative deflections. Incremental deflections are usually based on a 100-foot arc in the highway construction realm. And the deflection of a 100-foot long arc is 1/2 of the degree of curvature. D here stands for the degree of curvature. 1/2 of the degree of curvature, which is 6 degrees, 57 minutes, 27 seconds. Half of that will give us 3 degrees, 28 minutes, and 43.5 seconds. Here I have elected to round my seconds to the nearest half second in order to mitigate the majority of intermediate rounding effects. A useful deflection for us in our computational process will also be deflection for 1 foot of arc. Now, in reality, we're not likely to lay out every foot along this 920-foot curve, but it is a good intermediate step that will shortcut our work over the next several slides. So the deflection of 1 foot of arc, as you can see, gives us a very small number, 0 degrees, 2 minutes, and 5.24 seconds. Many of the stations in the curve fall at whole 100-foot stations. However, there are points that are not separated by a 100-foot arc. For instance, from the PC to the first 100-foot station is something less than 100 feet. Likewise, the arc midpoint falls somewhere between 2 100-foot stations. And at the end of the curve, there is a 100-foot station that falls some odd distance before the PT. Those odd length arcs require that we use that 1 foot deflection. So if we need to calculate the deflection for that first station from the PC or any other odd station along the curve, first we'll compute that arc distance from the last point with the known deflection to the station you're calculating. Then we'll multiply this arc distance by the deflection we just calculated for that 1 foot arc. This will give you the deflection between those 2 points. For instance, if we're finding the deflection angle at the first regular station, that first regular station occurs at 54 plus 00. Our PC is at 53 plus 22.84. So we take the difference in those two stations and come up with an arc length of 77.16 feet. 77.16 feet times the deflection angle for 1 foot of arc will then give us a deflection of 2 degrees, 41 minutes, 4 seconds. So that simply means when we're sitting at the PC and we need to turn the angle and measure the distance to set point 54 plus 00, we're going to turn an angle of 2 degrees, 41 minutes, and 4 seconds. We'll calculate the distance, the chord distance, in a little while. We need to compile our incremental deflections. What I've done here is set up a table that would normally go in your field book if we were doing traditional curve layout like this. And you'd list the stations. At the first station you have at the top is the PC station, followed by whole 100-foot stations. And then at the arc midpoint, we have calculated that arc midpoint, that is, that point on the arc halfway between the PC and the PT. And then the remaining 100-foot stations, and then the PT. You can see the arc distance of 77.16 feet is that arc distance from station 54 plus 00 back to the PC. And then from 54 plus 00 to 55 plus 00 is an arc distance of 100 feet. If you summed this arc distance column, it should equal the total arc distance of the curve. The incremental deflection to 54 plus 00 was the one we just calculated, 2 degrees, 41 minutes, 4 seconds. Then the incremental deflection of 3 degrees, 28 minutes, 43.5 seconds, we calculated just a few slides ago, and you can see it applied multiple times here. Every place that I have an arc distance of 100, you can see that deflection angle showing up. Down at the tail end of the curve, I had a 42.70 foot arc to get from station 62 plus 00 down to the PT with an angle of 1 degree, 29 minutes, 8 seconds. Once I have computed all my incremental deflections, then I can sum cumulative total deflections. The total deflection at station 55 plus 00 is the incremental deflection from 54 plus 00 summed with the one from 55 00. Notice down at the end of this column that the total deflection to the PT is 32 degrees, 0 minutes, 0 seconds. Well, that makes sense because that is delta over 2 in our case. Remember that delta was 64 degrees. Well, the deflection, the total deflection from the PI to the PT is half of the delta angle. So that would be half of 64 degrees, or 32 degrees in this case. So this confirms that our computations have been done correctly so far. Step 3 involves computing the chord length for each deflection angle. The chord that will take us from the PC to the point we're trying to lay out is simply equal to 2 times the radius of the curve times the sine of the deflection angle. This is the approach we use for what we call total deflection layout. Prior to the advent of total stations, we were pretty limited to what we call chord layout, or short chord layout, which simply required us to measure with a tape from a stake we had just set to the location we were trying to set. You can see in your text there are some examples of this, and We don't find so much value in teaching those processes anymore because you're less and less likely every day to use them in the field. Here's a simple example. Let's say we want to find the chord at the arc midpoint, the total chord from the PC to the arc midpoint. Well, it's simply going to be 2 times the radius, that is 2 times 823.50 feet, times the sine of the deflection angle that we computed for the arc midpoint, 16 degrees, 1 minute, 58 seconds. That gives us a chord of 454.88 feet. And you can see that 454.88 feet show up in the total chord column on this data. Notice that the total chord for the PT should match the chord length, the overall chord length, computed as part of the basic curve parameters. If it does not, then you've got a computational error. Likewise, this chord distance is shorter than the arc length. It has to be. It's a chord by definition. A chord length must be shorter than arc length. So if we recap how this goes in the field, with the instrument sitting at the PC that you see in the lower left here, we would turn an angle of 241.04 and go out a distance of 77.14 feet to set station 54 plus 00. Our angle increases by the amount of the incremental deflection angle for a 100-foot chord to go from 54 plus 00 to 55 plus 00. And as we continue, our deflection angle continues to increase by that 3 degrees and something that was our incremental deflection for the 100-foot arc. And we continue on around, and as we lay out this curve, we are taking longer and longer distances and regularly increasing deflections. When we get to the end, the deflection angle to the PT is equal to half of the delta angle. So there's some computational checks, and I've mentioned these a few times already, but they bear repeating. They will help you avoid errors and check yourself so that you won't get surprises in the field. First of all, the total deflection at the PT must equal delta over 2. That is, when you compute it, the cumulative sum of your incremental deflections should bring you to delta over 2 at the PT. If it doesn't, then you need to do some troubleshooting. The computed chord length to the PT must equal the long chord C, that is, the curve parameter C that we computed at the beginning. And of course, this is less than the arc length. A chord, by definition, is a tangent figure that crosses 2 points on a circular arc. In the field, there are some things we need to do to check the work, and first of all, if your PT and your PC and your PI have already been staked, maybe you have already staked them or they were staked by someone else, first you should occupy the PC or the PT and measure that angle that would give you delta over 2. You need to check that to make sure, first of all, that you have your instrument in the right place and that indeed this is the curve you intend to stake and that the computed data matches the information on the ground. Then, measure the distance from the PC to the PI. That should be your T distance. Then measure your distance from the PC to the PT. This should be your total chord. That is the long chord that you calculated in the beginning of this process. As you stake the curve, it's wise to stake the midpoint. Then once you've staked it, before you move past that, use a tape and measure the offset from the arc midpoint to the PI. This needs to equal the E distance, that is the external distance that you calculated at the beginning. If there is not reasonable agreement between your measured e-distance and your calculated e-distance, this should give you sufficient pause to investigate the cause of the error, determine whether it's a physical measurement problem or a computational problem. Error management applies to not only your computations, but your field work. Therefore, avoid intermediate rounding during computations. You will find with experience that there is a degree to which you can truncate your numbers without having a significant impact on the final result. And remember that in the field, the control points that you use do contain some positional error. If they were placed by humans, yes, they have to have error in them. So the positional errors of your control points will affect the closure of your layout work. If you start by occupying the PC, set 0 on the PI, and turn deflections and run in total chords for all your points, when you get to the PT, there may be some misfit. Hopefully you've determined what that may be by some of your initial field checks. And of course, the intended use of the layout governs the limits of acceptable error. For instance, if you're laying out a horizontal curve for a highway, you want to do reasonable work, but in the real world, in the profit-oriented world, our motto is often go fast and make money. Is it reasonable to try to get 2/100ths closure on highway centerline for asphalt pavement? If you've been around asphalt paving, you know that it's a rather imprecise process, steering the paver and getting the compacted mat to a specific width. In that case, you may find that if you have a couple of tenths misclosure at your PT, then you're doing fine. One of the things we sometimes joke about is once the asphalt is cool and the surface is smooth, the cars won't care about that couple of tenths misclosure. Likewise, in the railroad world, with alignment machinery that has the ability to detect fairly fine misalignments using laser equipment, that alignment equipment has the ability to work out imperfections in the layout. Let me give you a story. Years ago, I was helping a couple of senior technicians lay out really a double reverse curve to reroute the old railroad tracks in the south end of Champaign over the bridge above Windsor Road. So there's a north-south rail line crosses above Windsor, just immediately east of Neal. And that curve has a spiral curve spiral transition for each portion of this double reverse curve. So there's 2 spiral curve spiral transition sets at the north end of the bridge and 2 more at the south end of the bridge. So that's a total of 8 spirals and 4 circular curves. It was computationally kind of challenging. Fortunately, I wasn't doing the computations, but I was the guy that had to drive the pins in the ballast and get this laid out for the railroad crew to move the track in. Well, we were out there laying it out and having a bit of a frustrating time getting points marked because of trying to penetrate the ballast with a half-inch iron rod. Kind of challenging. We were slaving away, and someone from the railroad came along and asked us what we were doing. Told them, well, we're laying out this curve so you guys can get it run in. They said, oh, just get it within about a half a foot. There's no need for you to get real crazy about it because our alignment machine will detect all the misalignment and realign it to what it's supposed to be. Point of all this is, depending on how the folks that need the information are going to use your layout, the accuracy you use can vary. If you're doing boundary work and you have several points along a curved right-of-way that have to be set, well, that may actually require higher accuracy than you might have to have for paving an asphalt road down the middle of that right-of-way. So it's important that you recognize the intended use of the layout governs the limits of the acceptable error. When you walk away from the project, you may have a highway looking like this. There's something satisfying about running in a circular curve, and I think you will find that an understanding of all the parameters and the layout Takes a lot of the mystery out of how that actually got there.